Okay, and here is Thomas Wiegart to present part 2 of joint forward error correction and probabilistic shaping with polar codes. Go ahead, Thomas.
Okay, thank you, Rick. And so, yeah, welcome to the second part of my talk. I think I have less light than last time, so I'm open to even more discussion. So I think I'm not going to need that hour. So we should have a lot of time for discussion. Okay, so let me directly start with a very brief wrap up of part 1. The first thing I want to wrap up is, polar code basics and some notations. So polar codes, I guess you still remember from last time or already know them, but they are linear block codes and they are always based on this 2x2 transform, which is recursively extended. Just some notation, we have U, which contains our data. Then the code word we denote by X, we transmit it through a channel, and the received word is denoted by Y. And the nice thing about polar codes is you can decode them successively with a successive cancellation decoder. And at position, when decoding position E, the decoder computes the probability of bit UI given all the previous bit decisions and the channel output Y. And then these probabilities actually polarize. That's what or where the name polar codes comes from. And namely it polarizes in a way such that the entropy of the bits UI given previous bits and the channel observation is either very close to 1. So that's kind of bad because that means this bit is uncertain, we can't decode it, or it's 0, that's good. It's kind of, there is no uncertainty anymore in this bit, so the decoder can decide on what it is. And then the trick is to just freeze the values where the entropy is high, set them to a value that is known at the encoder and the decoder, and then use the other part for data transmission. And yeah, the fraction of bits that is bad is the entropy of X given Y. So actually the fraction of bits that is good is 1 minus this entropy. So in a binary symmetric channel, that's the capacity, and polar codes are capacity achieving. Okay, that's part 1 of the wrap up about just classical polar codes. Part 2 is how to create polar codes with a non-uniformly distributed code word. So I guess that's also the picture where we spent the most time discussing in the last part. So yeah, the first row here we see is the standard polarization for uniformly distributed code word. So you have some bits that are bad, and these I denote by calligraphic F. So that's our set of frozen bits. And these bits can't be decoded from the channel output, so we can't use them. Now, if we want to create a code with some distribution, then we have another polarization going on. And we have some bits where we can't put in data in order to generate our code word. These are these bits over here. And well, so they also can't hold information, but we have to set them somehow depending on the message that we transmit such that we can generate the code word. And what's remaining is here this intersection of the 2 green areas. And these positions we can use for transmission. And transmission is actually equal to the mutual information. So that schema is actually capacity achieving also on asymmetric channels. And yeah, we saw that we had quite a good performance just for on-off keying. And now part 2, we will ask the question, what happens with higher order modulation formats? So if you want to go to 4 ASK, 8 ASK, or so on.
May I ask a question?
Yeah, sure.
In the top row, it's H of UI given UI minus 1 and Y. And so it's good if if it goes to 0, it means that if I know the received value and those previous U's, then I know that U. Now, in the bottom row, I think there are sort of 2 questions. I guess the most important one is, shouldn't there also be an X there, that it's H of U given the UI minus 1s and X because it's only given a specific code word, or do you understand what I'm saying?
Not X, but it's of course depending on the distribution that you want to generate.
So you're requiring that that X be in the distribution. There's something. Some
Well,
constraint.
I mean, there is like a linear transformation between U and X, right? So it's
Right.
like if you know all the previous U's, then you also know the X at least up to this position.
Got it. Okay. And I was just wondering if the order was wrong, if it's like, because in one case you're saying I minus one, but you're coming from different directions. So there might be like a little bit of a subscripting detail.
No, it's all successively starting from the beginning.
Got it.
And so, I mean, that notation here means like that's the vector from 1 to I minus 1. So it's always like,
I see.
just
Yes,
the notation here with the double
even though the
brackets.
reds are showing up at different ends of the graph, it really is always in the same order. Okay.
Yes.
So the answers to my questions are the indexing is right, just the way it is. And you don't need to have an X because given the distribution, given the code, really the first UI imply the X. So I don't need to have the X extra. Explicitly. Okay, thank you.
Okay, good. Then, yeah, let's start with part 2. So the way that we are going to do higher order modulation is by using multi-level coding. So for some reasons, which I will talk about also soon, let me just start with some literature. So, I mean, multi-level coding in general came up from Gottfried Ungerböck in 1982. Yeah, then, well, for polar codes, Seidel and a group, like he's from Johannes Huber's group in Erlangen, also not too far away from Munich, actually. So they considered polar codes for high order modulation, and like they looked into multi-level coding, they looked into bit interleaved coded modulation, and they basically found that polar codes perform very, very well with multi-level coding, and actually way better than just doing bit metric decoding. Yeah, then some follow-ups maybe like from TOM, 2 papers, like one from Georg is about how to do code design for multi-level coding and polar codes, and already contains some implementation tricks. And then my colleague Tobias, he did password polar codes using multi-level coding. And yeah, what I'm going to present in this part is something from my colleague Konstantin Runge. So he basically did that for his master thesis that I supervised or co-supervised. And yeah, the scheme is called multi-level Honda Yamamoto coding. So Honda Yamamoto, these were the guys inventing the idea of shaped polar codes. And yeah, we're going to extend it here to multi-level coded modulation for symmetric and asymmetric channels. Okay, so yeah, for multi-level coding, let me maybe just start with a brief example and a brief introduction to show you how it works before I get formally. So let's look at the example where we just have 4 channels and we want to have 8 ASK, an 8 ASK constellation. So that means every symbol that we input into the channel needs to be labeled with 3 bits. For polar-coded higher order modulation, one usually always uses set partitioning labeling. So that's basically comes from the Seidel paper. They found that set partitioning works very, very well. And the way it works here with polar codes, now that we have 3 bits per symbol, we take 3 polar codes, and then from the first polar code, we always use the first bit of each symbol comes from the first polar code. Then the second bit of each symbol comes from the second polar code, and the third bit of each symbol comes from the third polar code. And well, for decoding, we first decode the first polar code, and then given the decoded values of the first polar code, we demap the bits for the second polar code, and well, then for the third, given the first and the second polar code. So a bit more formally.
I have a question.
So, yes, sure.
I didn't understand what is the input and what is the output here very clearly. So,
so the input here is on the left is U. Of course, in this U, there are still some frozen bits and then later also some shaping bits. And the output is X. So X1 to X4 are the symbols that we transmit.
Thanks.
Okay, so a bit more formally. So each symbol xi we label with m bits, and we just denote it by xi subscript b to denote that that's the binary representation. And then we can view every bit level as a separate channel where we have some side information, namely side information from the previous bits that were already decoded or at the encoder already encoded. And yeah, for decoding, we do multi-stage decoding based on the chain rule of mutual information. So first, given the channel observations, we decode the first bit level. So that's the first polar code. Then second step, we decode the first polar code, the second polar code, given what we decoded for the first one, and so on and so on. And yeah, so now the polar code specifics. So each bit level we protect with a separate polar code. And when we do code construction for these polar codes, actually what we do is we chose the frozen set and the information set and also the shaping set later. We determine that jointly over all polar codes. So we determine the reliability of all these bits jointly and then do code construction jointly over that code. So we don't have a problem at all of the classical problems of multi-level coding that you do need to do rate allocation between the codes and so on. That just comes naturally and is not a problem at all here. And yeah, for decoding, we not just only use successive cancellation decoding, but successive cancellation list decoding. And what we further do is that we pass the list between the bit levels, and in the end, we do a CRC check over the whole code word. So it's more than just having three separate codes, because the list decoder goes through them jointly, and the CRC to prune the list in the end is also jointly over kind of the big code. Okay, so that's for the kind of uniform part. So far, any questions to that?
I have things I want to say, but I'm gonna wait. I just thought of
No.
something.
Then go ahead. Go ahead.
Oh, well, if you go back to your picture, it's a beautiful picture. Yeah. So, I spoke to you earlier about how we could do coding for Flash. And it seems like this is perfect. All we would do. So right now you take for example, well, it doesn't even have to be net equally spaced. Your 8 ASK could be anything. But in your current formulation, you don't care that the polar codes have the same rate. They could have different rates. It's all fine. You're going to change the number of frozen bits. It's very easy. But for the Flash application, each of the polar codes would actually be coding a different page of Flash memory. And they actually would be required to all have the same rates. But it would be super easy for us to do that. That's the part Samira has solved. And so we would just be doing exactly this design, but with a slightly different constellation, where it turned out that all your polar codes were the same polar code. And it's just sort of proving that actually you could have the same polar code with very little loss or no loss compared to the perfectly rate variable solution. That's all I wanted to say.
Okay. Yes, I think we should talk about it if we can easily use the polar codes for the Flash problem that you have.
Good.
Okay, then let's go back to shaping again. and to the so-called multi-level Honda-Yamamoto coding. So, well, what we can of course do, let me maybe go back to the picture. We can do Honda-Yamamoto coding for every level and just do it independently, right? And that way we could rather easy generate a product distribution, because if we do, if we shape these polar codes independently, then we can only generate a product distribution, but we can't generate an arbitrary distribution. And that's where multi-level Honda-Yamamoto coding comes into play. So the idea that we had here is, so still we use the shaping for like every bit level, but we can actually use the previous bit levels as additional side information at the encoder. And then of course also at the decoder. So instead of like previously, when we just looked at one polar code, we had the entropies ui given previous use and the entropy of ui given previous use and y. We now analyze the entropy of ui given previous use and the previous bit levels. And the second one is ui of a certain bit level given previous uis of this bit level, previous bit levels, and channel observations. And it turns out that this actually also polarizes just as well. So by treating the bits that we already encoded as side information, these bits then of course change the distribution that we want to generate, but it's fine. It's just side information which is known at the encoder and decoder. And this polarizes as well. And so what Consti was actually able to show is that like each bit level can approach the rate mutual information of the x of this bit level to y given the previous bit levels. So I mean that's kind of the entropy of x given previous bit levels minus entropy of x given previous bit levels and y. He could show that we can approach this mutual information with some error exponent, and then if we combine all bit levels, he basically showed that with multi-level coding and this Honda-Yamamoto scheme, we could still achieve capacity of like any well, non-binary input, symmetric and asymmetric channels, basically.
Thomas, I have another question. I'm sorry.
Yes.
Can you go back to your picture again? Because you said something and it actually, okay, so you pointed out that each of the bits of the set partition labeling is coming from a different polar code. And so you're only allowed to have set partition distributions that can be produced as product distributions of, call it P1, P2, and P3, right?
That's if we would shape the polar codes independently.
Yes. Oh, but you're not going to do that.
Yes. So I mean, you can do that. Then you can of course only create product distributions of the set partitioning label. But
yeah. Did you
so
look into
we start with
of that, like how close you can get to an optimal distribution with set partition labeling, with the distributions being independent?
To be honest, I never fully checked. I remember like doing some small examples, and there it was kind of okay, so not too far away actually.
Right.
But like, I haven't done a complete study or so.
Okay, no, that's fine.
I guess that might be interesting to look at as well. Yeah, so maybe.
Well, for the flash problem, that is the constraint, because the different pages, you wouldn't be able to do it dependently. Anyway.
Okay, yeah, but I think it doesn't hurt too much. But
can you tell me how you shape it so that they're not independent? I missed that.
So we start by shaping the first bit level, so polar code 1.
Oh, I see. That's what you, so okay.
And then we know the realization of these single bits, right? And that gives us a distribution that we want to generate for polar code 2.
So you use a different, it depends on the specific instance of the code word?
Yes.
Okay,
So it's like, for example, if for the first symbol, the polar code symbol here is a 1, then probably in the first symbol here, we want to have a 0 with probability 0.6 and a 1 with probability 0.4. Whereas, for example, if for the second symbol that is a 0, then we want the distribution flipped, for example, and want to have a 0 with probability 0.4 and a 1 with probability 0.6.
okay, got it. Thank you.
So yeah, that's actually the big thing here, that we adapted to what happened in the previous bit levels, and this can generate any distribution basically. Okay, any more questions about the scheme? Because if not, then yeah, let's go on to again finite length results. So again, we showed it's capacity achieving, but who cares if it's achieving capacity very, very slow, right? So let's again look at finite length performance. And as also for part 1, I just start with performance for distribution matching. So we again have no channel coding part. So the frozen set is just an empty set. And we just try to use the polar code here to generate a code word with a distribution. To do so, for encoding, we again use successive cancellation list encoding with a list size of 32. The target distributions that we want to generate is a Maxwell-Boltzmann distribution, and it's just characterized by the entropy. And yeah, what we do for like different symbol cardinalities. So first we try to do have an output cardinality of 4 symbols, and we try to achieve a entropy of 1.6. Then for 8 symbols, we try to achieve entropy of 2.4. And for 16 symbols, we try to achieve an entropy of 3.3. And again, we consider the rate loss, which is the difference in entropy of entropy of the empirical distribution minus the target entropy. And what we get is the following. So we again compare to CCDM. CCDM here now, that's for a cardinality of 4 symbols, is the yellow curve, and multi-level Honda Yamamoto is the blue curve. And now, well, actually, in contrast to the binary setting where polar shaping was just definitely worse than CCDM, now we're actually better in like a range of very short code words. And well, the range here is up to, I think that's like length 64. So CCDM actually gets way worse when you increase the output cardinality. But for the polar codes, that doesn't seem to be the case that much. And we also see that when we go to even higher cardinalities. So if we now go to cardinality of 8 symbols, then CCDM jumps quite a bit, whereas the polar code, well, of course, gets a bit worse. The rate loss gets higher, but not too much actually. And now if we go from 8 to 16, CCDM makes a big jump again, whereas the polar code doesn't change too much anymore actually. So here we can kind of already beat CCDM a little bit. So in terms of rate loss, the polar code seems to be not too bad if we want to generate an output symbol, output alphabet with a lot of symbols actually. Then CCDM loses a lot of performance per bit of output cardinality that you add, whereas the polar code doesn't matter too much. Okay, that's the.
Do you want to talk about why the CCDM is so limited? I mean, is it because basically, you know, you're fixing yourself with a particular empirical distribution, but really you need multiple such, like a multi, I know Lin Fong used multi-composition distribution matchers for ATAM, that you're just, it's too restrictive, the constant composition alphabet?
Probably, yeah. I mean, the more symbols you have in your output cardinality, right, the more restrictive you get with the constant composition. I guess that might be the case, yeah.
Yeah.
And I mean, like here, that's if you're in a block length of 100 symbols or so, but have 16 different symbols and want to generate a something with a constant composition there, then that's pretty restrictive, right? So I guess that might be a reason for that, yes.
Anyway,
So-
great.
Oh.
Go ahead, Lev.
I don't know if I'm recalling this correctly, but in the binary case where you showed us the rate loss, did it also have a similar kind of plateauing effect as the code length increased? Or is this, can you remind me?
No, so I mean, so, well, first of all here, the y-axis is not logarithmically, right? So it's going down to 0, but it's not easy to see here. But yeah, the polar code is definitely going down slower that we see. Like if we would plot it logarithmically, then the CCDM is just a straight line. At the polar code, the slope decreases.
Okay, so this is not logarithmic, so
And
it is going to 0. It's not plateauing.
Yeah, it's going to 0.
Okay, but the CCDM is, well, actually, no, the CCDM goes faster to 0 than yours.
Yes, the CCDM is going faster.
Yeah, but at the lower lengths, it's much better. Okay. Another question I have is, so if you go back to the Honda-Yamamoto coding scheme, you're trying to hit the distribution for, go back to the figure again, actually, the figure is probably better to discuss. Yeah, this one, yeah. You have a target distribution for the X's, right? And you're translating them into a target distribution for the intermediary bits, right? So you're just trying to hit the independent bit probabilities, but are you looking at them jointly? Like, for example, for X1 to have some probability of hitting a symbol, all 3 of them have to jointly do it? Or do you just try to get the probability for each one of them individually, the bits?
No, we are doing that jointly. So
you're doing it jointly. Okay, so it is that.
Yes, so it's successively. So we decompose the probability into probability of the first level times probability of the second bit level given the first bit level.
Okay.
Times probability of the third given first and second bit level. So that means we first generate some distribution on the first bit level. And then given that distribution that we have, we generate a distribution for the second one.
So interestingly, when you see the frozen bit selection and the shaping bit selection, I'm presuming that PC1, PC2, PC3 have a different number of each of them. So some have more frozen than others. Does that come out in some sort of difference in, like, decoding complexity? Like, for example, PC1 is no frozen bits. Now you're essentially doing a full polar code decoding, and then you're going to send a big list to the next one. Is that any kind of bottlenecks, or have you not seen that kind of issue?
I would say rather not. So I mean, the polar decoder, like complexity of standard list decoding doesn't really depend on how many frozen bits you have, right? So I would say it's more or less rate independent.
Is it? Okay.
It's probably a bit like a little bit better if you have many frozen bits, because like when you have a frozen bit, you don't need to branch the list, right? So in that sense, it's less complexity if you have a low rate code. But
and how? Okay, so I'm just thinking about the. Okay, that's it for now. I'll think of something else in a bit. I had the
okay.
Yeah, go ahead. Anybody else?
I do have a question. It seems to me, so that's part of the question, that you are doing this joint format to have a single system, like maybe for lower complexity, or maybe like is it just better performance on certain regime? And the following question would be, if it's like a simpler system doing this joint shaping, how much complexity does the successive cancellation list, so the listing adds compared to what you gain rather than using the single shot successive cancellation?
So it's complexity wise, it's linear in the list size. So cranking up the list size is somewhat feasible.
Okay, and the overall complexity, how does it compare to the, I forgot the name of the other scheme, the YH, the Yamamoto scheme, I guess, right?
Yeah. Well, I mean, you of course you increase the complexity of encoding, because at the encoder for that scheme, you need to run a decoder. So I mean, asymptotically, standard polar encoding can be done in big O of n log n, and successive cancellation decoding also needs n log n. But of course, the decoding is way more complex than the encoding usually. So the prefactors are way higher for the decoder.
No, my question is
we add the decoder at the encoder. So
the overall complexity.
If you say you ignore complex.
Okay, compared to the alternative, so you have curves for two systems, the one that you're developing and the Yamamoto scheme, right?
No.
In the figure.
On the Yamamoto scheme is what I'm using.
Oh, okay. And what are the two schemes in the graphs, the performance plots?
That's the multi-level Honda Yamamoto, what we are using, and CCDM, which is constant composition distribution matching.
Oh, okay.
So it's right now it's only for distribution matching, so only for generating some code word with a non-uniform distribution out of uniform message bits. And CCDM is just like the one of the well-known distribution measures, and CCDM is what came with PASS, basically.
Okay.
So
that is my question. How does the complexity of your scheme compare to CCDM?
Good question, because I never implemented CCDM myself.
Okay.
No, I can't give a good answer on that.
Okay, thanks. Yeah.
Building off of that, do you actually have error plots for like a channel application, or is this just purely you're calculating the rate loss for the Honda Yamamoto scheme?
Well, for like the distribution matching is just generating a code word, so all you could look here is the rate loss, how good can you generate the distribution? But yeah, the actual error plots, that's like my next and last part, where we used it for end-to-end simulation. So
you had more. I'm sorry, I didn't know.
Yeah.
I'm so sorry. I thought we were just in the discussion phase.
No, it's fine. Okay. So yeah, I mean, the big advantage of the scheme is, of course, that you can do it jointly, right? Generate a distribution and have it as a code word of an error correcting code. So the CCDM can just generate something with a like desired distribution, but you can't transmit that over a channel. Or, well, of course you can, but you have no error correction in there.
But
the big advantage is to do it jointly, like to generate a distribution and to do error correction.
Yeah, then I'll just let you show us. Yeah.
Good. And yeah, so for that case, I looked at two scenarios. The first scenario is a symmetric one where we have 8 ASK, so plus minus 7, 5, 3, and 1, and a Maxwell-Boltzmann distribution. So the distribution on the points looks something like that. We have 64 channel users and an overall transmission rate of 1.75 bits per channel use. And then the second scenario is a asymmetric one, where we use 4 pulse amplitude modulation. So we have 0, 1, 2, 3. And the distribution, the optimal distribution that we get here under an average power constraint is a asymmetric distribution, which looks somewhat like that. So that's a distribution that you can't generate with standard pass schemes. So that's where only our scheme works optimally. But what we do here to compare it to pass, we could actually just generate a symmetrized constellation and then use that constellation, because here we have a symmetry, so we can again use pass. Okay, so for the first scenario, this is what we get. So first of all, the red dashed curve is uniform multi-level polar codes. The blue curve is what we get with multi-level on the Yamamoto, and what's SNR over, or frame rate over SNR. We get a gain which is like somewhat close to what we could expect from capacity. And yeah, so some comparisons. So the yellow curve here is polar coded pass. So it's a symmetric scenario, so you can of course use probabilistic amplitude shaping, and that's the comparison curve here with polar codes. We can actually beat it a little bit. Some bounds, so the random coding union bound, we're like on top of it or a little bit better. Sphere packing bound, we're a bit far away. And yeah, actually the only thing that can beat it is if we ask Ling Fang, and we get the green curve here I just got yesterday from Ling Fang. So he was able to beat it, but I still think that the polar codes scheme is pretty good. So I mean, Ling Fang beat it with the TCM pass, but he actually used a way larger list size. So probably like now it's up to us to beat the green curve again. So we maybe need to care more about code design and list size and so on.
Well, that would be a fun thing
so,
for you to do while you're here, Thomas, as a side project, is to work on beating, getting the polar code to be as good as Lin Fang's TCM pass.
yes. So to defend the polar code a little bit, I mean, we optimized the size of the CRC, but we didn't optimize the CRC polynomial itself. So we just tried some from tables, but the only optimization
I know
is
a guy.
try different CRCs. And I guess Lin Fang optimized the CRC. And yeah, so CRC and list size, I guess we could still hope for the polar code.
So Thomas, that's a great idea. While you're here, maybe we could optimize the CRC and see how that changes things.
Yes, we could give it definitely a try.
Actually, Han-Wen Yao is actually postdocing with Henry Pfister, but he's willing to help us out with some things. And he's our guy for CRC design for polar codes. He helped us with the I presented to Qualcomm. He was the polar part of that. So maybe we could, if you're interested, we could set up a Zoom with the three of us and see if it's low enough bandwidth for him to go ahead and do that, to be on a joint paper. And if you picked up the other, I guess we're talking about like 2 or 3 tenths of a dB. If that's what made the difference, it would be interesting to know.
Yes, yes, definitely. We can give it a try.
I have another question. It seems to me from your previous plots that you have a rate gain in it seems that regime of 64, you have a rate gain. So why did you plot SNR instead of EBNO?
Yeah, I could also plot EP over not, but to compare the curves, it doesn't matter because all the curves are at the same overall rate, right?
Oh, okay. So you have the same rate for everyone here.
Yeah. So it's all the same rate. Otherwise, the comparison wouldn't be fair.
Okay. Yeah, that's exactly the question. Thanks.
So yeah, it's just a constant shift of all curves. So it doesn't matter. And yeah, maybe one more thing to remark here is like the different size of the CRC. So for the multi-level Honda Yamamoto, we actually need a larger CRC, whereas polar-coded pass and also Linfang have a smaller CRC, and that's because they have both of the schemes use a distribution matcher where they can actually use the distribution matcher constraint as an additional list check. So polar-coded pass uses CCDM, and the constraint of the CCDM, namely that you have a constant type, is also used to prune the list, and the same holds for Linfang, and that's why the CRC here is smaller.
I think that's really fascinating, and I agree with you. That's exactly the way to understand Linfang's smaller CRC. We haven't done the math. It would be interesting to consider the effective CRC size of like Linfang's 2-bit or your 3-bit and the constraint on entropy of the distribution matcher to say, oh, well, our 2 bits plus the distribution matcher is effectively exactly the same as a 7-bit CRC, or really it's a 6-bit or a 9-bit. You know what I mean? There's a understanding sort of the entropy constraint of the distribution matcher. That might be something that we could explore.
Oh, yeah.
One more
Okay,
question.
good. Then, yes.
In the green curve, is that a list size
Yes.
5,000 with a 2-bit CRC?
So it's Linfang uses an automorphism decoder, so he runs 5 parallel decoders, and each decoder has a list size of 100. That's what it's saying.
Okay.
So
And
the CRC prunes a list of size 100, but Linfang has 5 of them.
how does the size 100 list help when the CRC is only 4? So it seems to me that it's only like 4 possibilities. I mean the spread 2 to the 2 is 4.
This is Amael, it's connected to what Thomas and I were discussing earlier. So the CRC is used to tell you whether or not your code word is in a list of possible valid code words. But in these schemes, there's this other module, the distribution matcher. And when you decode a code word, it may not be a valid code word according to the distribution matcher. So really it's far more of it's not just the 2-bit CRC where every 4th code word has to pass it. It's also the distribution matcher. And that was what I was just mentioning to Thomas, is that we could do the analysis and figure out like, what is that like what fraction of code words pass the distribution matcher, and therefore how many bits of distribution matcher CRC are there as well. But I can guarantee you it's more than, it's not just a 2-bit CRC. So the large list, it makes sense.
That makes a lot of sense. So if I understand it right, you have so much checking power on the distribution matcher that you only need to combine it with a 2-bit CRC to have enough of a check to discard a lot of the bad code words, basically.
Exactly. Yeah.
Yes.
The 2-bit or 3-bit in the case of PC Pass, those CRCs are really just polishing what is already a pretty shiny diamond. It's just the last little bit.
Thanks. That explains a lot.
Sorry, Thomas, I should let you answer that question.
No, it's fine. So yeah, and actually, so I mean, if we go back to the rate loss, we see that the CCDM has quite a high rate loss, and that's because of this constant composition constraint, which kicks in a lot for short blocks. But on the other hand, we can I see it kind of as recovering a little bit of this rate loss, because we use this constraint at the decoder, so we kind of at least don't waste this rate loss completely. And I mean, adding a CRC is also just rate loss, right? Because the CRC doesn't help you for the code. It just helps you for picking the right element of the list. So it helps you for the decoder, but in the first place, it's just a rate loss. And well, that's the same with the CCDM. It gives a high rate loss, but you can use that one to improve the decoder again.
Hey, Thomas.
Okay, good. And yeah.
Oh, is there more? Sorry. Yeah.
I have one more result slide.
Okay, well, finish that and I'll ask my question afterward.
Okay, good. So the second one now is the asymmetric setup. So where we have for pulse amplitude modulation. And here, red curve is uniform polar code. Blue curve is what we get. And the yellow curve here is the symmetrized pass. And there, okay, of course, we see we can beat the symmetrized a bit. But what you actually need to note here that all of these curves are without any CRC. So we just use plain list decoding. And now if we add a CRC, then polar coded pass can like get a little bit out of the CRC. But actually, really, so far we weren't able to get anything with plain list decoding. Plain list decoding was better than list decoding with the CRC. So the CRC only gave us a loss so far. So I mean that's still kind of a bit of a open problem, and I guess it's like a code design problem. We need to maybe either like find a better code.
Your
okay, yeah,
internet
so
is a little bit unstable, or at least it was for me.
Sorry?
I missed your last couple of sentences. Your internet seemed to cut out.
Oh, okay. So then I don't know where I stopped, but so the point I was saying is that like all these curves here, they're all list decoding without CRC. And the polar coded pass, of course, gets a little bit better when we add a CRC. But for the blue curve, for our multi-level Honda-Yamamoto scheme, we couldn't find a CRC that actually improves the curve. So we're still that's still a bit open and like a little bit of a mystery to us. What's going on here? If it's just a code design problem, so maybe we just need to find a matching CRC, which is good, or maybe we need to find another polar code design here or so.
Can I ask you, Thomas, you're plotting versus SNR, so are you including the hit you would take in rate because of the CRC in your PC Pass 3 CRC plot? Or
yes. So
is it actually, is it SNR or EB over N0 on the x-axis?
It's SNR, but when we add like this 3 bits of CRC, we always remove 3 bits, 3 frozen bits. So it's always the same overall transmission rate.
Well, and that could be part of why you're not seeing the improvement in the Honda Yamamoto scheme, because sometimes you add, when you're unfreezing those bits, you're unfreezing reliable enough. They're unreliable enough that actually it was a mistake. Whatever.
Yes, that's kind of true, but it works for all other polar codes, right?
Right.
So the only fair way of adding a CRC is we still transmit the same message and we remove some parity bits from the code itself, because otherwise,
sure, absolutely.
Adding the CRC is just cheating.
I just want to, so Bruce and Lynn, I think also another thing, when I look at this slide, I'm saying, well, maybe we should give TCM Pass a try at this setup and see if we can come in below their current results. And that would be an exercise, Bruce, that you could do. So anyway, just a thought.
So on the symmetrized distribution.
Yeah.
Oh yeah, that would also be nice to be able to add the curve there. Okay, so that's basically what I have in results. So just conclusion, like we showed that polar codes give us a very clever way to do joint forward error correction and distribution matching. So we have the possibility to generate symmetric and asymmetric distributions. And yeah, the two nice things about it, that the finite length performance is quite good, although Linfang was able to beat us. So yeah, we still need to work on that. But on the other hand, we're also capacity achieving. So it's interesting both from theory and practice, I would say. And yeah, the big question, that's what we're working on now, is can we also generalize that scheme to other codes somehow, or can we find a similar way for LDPC codes, for example? So yeah, that's what Linfang and I are working on right now.
Which is very exciting. Yes.
Yes.
All right. Well,
good. So yeah, that's it. And now I'm open to more questions.
Okay, good. Let's see if we have more questions. I think I asked mine for, yeah, let's give some applause to Thomas. I'm going to do that too. Well done.
I think I interrupted Lev before, so he had another question.
I did, but well, first thing, great presentation. I really liked the work. I did have a bit of a question about how the list decoding is done in the Honda Yamamoto coding scheme. So you said that you first do all three in a row, passing a single list along until the end, and then you do the CRC check after the whole thing is done, right?
Yeah.
And because of this, you're using quite a large CRC, 7 bits, but couldn't you do some parts earlier? For example, you could have a CRC for each individual parts, and this will help you prune the list faster or earlier. So you could make larger lists at the beginning, prune them, become a shorter list as you progress, and now you could have a larger list size at different stages of the code. Especially, presumably, you have a lot of important information early on. You don't want errors to propagate because it seems like very similar to, like, you know, window decoding or multi-level decoding where errors can easily propagate. I'm just wondering if you've considered something like that.
No, not anymore. That's actually a good idea. So I mean, I once played around with it a little bit without shaping, so just using the multi-level coding and uniform code words. Mm-hmm. And there I tried out like adding a CRC for every bit level, but I couldn't get better in this case actually. So there's, I mean, if you use the CRC for a shorter code, then you also run into the problem like the CRC is already small, and now you make the small CRC even smaller by splitting it up into different code words. So probably you make the CRC even worse. So there I couldn't get anything out of it, but maybe it helps here in the shaping case. Yeah,
maybe there's also an argument to say, like,
point.
I think there's also an argument to make that it should be dependent on the number of frozen bits. For example, if that polar code have a lot of frozen bits, there's not a lot of wiggle room for you to be wrong. So maybe you don't need it at every stage, but like some stages it might be useful. I don't know. Yeah. 8 ASK is probably not necessary, but if you go to something even higher constellations, having those checks in the middle might be nice.
Yes, I agree. Maybe it's like, especially maybe for longer code words, it's where the few bits of CRC don't harm too much anymore in terms of rate. Maybe especially there it could help. Yeah,
that's definitely true. And I know you're talking to Professor Wessel about applications to Flash. But like, I think this could even be useful for stuff like magnetic recording, because if you're saying it could be work for longer code lengths, we're finding out that they really want longer codes. They want like 40K now at this point. We've heard from some industry people. So if you can make this work for longer codes, there's lots of other places that they can apply it to.
Okay, I think I lost a few sentences in the middle.
I'm also a mumbler. I'm a mumbler, so it's understandable if you misheard me. I'm just saying that there might be like some uses for this in like magnetic recording where they also have kind of like these asymmetric errors. Actually, how does shaping work? And maybe this is just a general question to the group here. How does shaping work for channels with memory? Does it help at all in those instances? Has anybody done that kind of stuff? The silence is nice.
Question. Maybe you also need memory in the distribution. I don't know.
Yeah. Sorry, just something to think about. I'm new to this topic. I do other things, so I'm just asking. But thanks for talking about this. Okay. I'm good.
Oh, Rick, you're muted.
Okay, I think we're gonna go ahead and conclude this recording. So I'm gonna stop the recording now. Thank you very much, Thomas. This has been a lot of fun.